I'm not sure. Yeah, I have here my own. Yeah, you can keep it. Good afternoon, everybody. I'm thinking what should be my first phrase to say. Probably to start with thanking organizers, because I think it's a kind of rather special opportunity to go back in time. And I'm also like to start with apology, because in difference with previous speakers, I'm not going to discuss physics, just kind of prehistory. I mean, maybe not a good idea, but still I'll try. I also think that not all this stuff is well known about, this old part. And let me try to start with pre-QCD about Khryplovich derivation of anti-screening in young males, 1969. Okay, Yulik, I mean, his official name is Iosif, but in family he was Yulik, so he's Yulik for everybody, after this time. And this is 69, my PhD was 68, but I was coming to the institute 62, so I was with him, very early on, first as an instructor, then the collaborator, and of course, always as a friend. So I try to remind a little bit, or to say a little bit about this, that, he was the one who was early on involved in this vector field theory. In particular, here it is the title of his paper in Soviet nuclear physics of 69. And to say about content, it's a little bit that he discussed this SU2 Young-Mills field, masses Young-Mills field, in he called radiation gauge, or for me it's more or less the same as Coulomb gauge, namely the gauge where, kind of you're putting transversality condition on vector field, three-dimensional transversality condition. And in this particular gauge, he calculated a Green function. And as you know, in the Coulomb gauge, you separated out instantaneous interaction, which doesn't depend on time, and there's a Coulomb law. And in this picture, it's marked by this dotted line. A dotted line, it's a Coulomb A0 component of vector field. And wavy line here, it is transversal component of the field. So you see that this particular feature of non-abelian Young-Mills is this, that you have this vertex which involves kind of nonlinearity is Coulomb field. So it's vertex which connects this transversal field and to Coulomb field. Okay. Now, when we consider, say, Green function in a particular polarization operator for zero component, and so that's why it is this D0, 0, I mean, this Green function. 1 over p squared is this normal Coulomb law. And here it is correction due to polarization operator. And there are two pieces here. One with coefficient 8 here, it is due to this diagram. And it is a diagram which contains this Coulomb field. And another part with a different sign, it is due to two transversal quanta. So, I mean, specific feature of this is that the first diagram does not have imaginary part, and second one does. And if you remember, this old story that of Landau zero and all the stuff, that the general argument was that you consider an imaginary part of polarization operator. It's a positively defined stuff related to cross-section, and that's why this kind of the existence of screening it is everywhere. So there is no exception of this. And here it was an exception of this rule. And you notice that it anomalies, however, I should say that in certain way it comes not fully appreciated. In terms of understanding that it could be asymptotic freedom of the theory, while technically Landau-Pomeranchuk, it's 1955. It was not was not unknown, but however, and I don't know. I actually should say that I put in blame on myself as well. I was there. And I could think better, I did not. So, okay. Anyway, but going back to history, it's even earlier. This was paper by Vainshtein and Terentiev, who considered electrodynamics of a massive vector field, charged massive vector field, and it is 1965. You see that Misha Terentiev, he was a native, and you see he died in his 60s. He was 60. He was also a very close friend. I'd like to say a little bit history of this paper, because Vladimir Vainshtein, he was in Dnepropetrovsk in Ukraine. And they were not associated in any way. They actually sent their papers to Journal Experimental Theoretical Physics independently. The editor who took attention to these papers was Yakov Smolodinsky. He saw those papers and said to them, to authors, united your papers. So you see here, you can see here that submitted June 13, he submitted October 10. So they wrote it together. So in this way became acquainted one to another, and it was published in this form then. It's how to say, you can see that they also notice anomalies character of just elimination. They notice there, and for me it's a little bit puzzling because you see, particular Misha Terentiev, he worked in ETEP, and I came there. During my graduate study, my PhD advisor was Boris Yofe, but when I came, Pomeranchuk was alive, and you see, it was crucial, his attitude to this, and he did not believe, this theory. No, in particular, this theory was not normalizable, right? So kind of. However, in ETEP, to send paper somewhere without endorsement of Pomeranchuk was impossible. I would not imagine that it would be possible. You see, it's a different character of interaction within a group. Misha managed to send his paper. Then it was this unification with Vainshtein, so it means that kind of it was maybe, I don't know, maybe it was some mixed feeling for Chuk. I'm not sure what was the reason, but anyway, it went through, and you see, they actually calculated not only polarization, but also you see that it was like has-been a Lagrangian. So they calculated one loop contribution to, a different number of external photon lines. Okay. Okay, so now I'm going to the next piece of history. So where I also took participation, and it's again about vector theory, but particular massive Yang-Mills theory, and our with Yurik kind of attention to this theory was initiated by paper of Tini Weidman, who suggested that kind of massive theory could be normalizable. No, I mean, okay, if you look at his, say, abstract, you see the investigation presented does not exclude the possibility that the theory is generalizable. So it's softly shaken. Okay. But for us, it was a kind of, moving force, because it was, in the literature, it was kind of different kind of attitude to this, so we tried to check it out. I mean, so, okay, now, no, not much of formula, but still. So, as you know, that kind of in this Parka formalism for massive vector field, you know that there is a singular behavior. Yeah, I see. Okay, but if I will fall down, it would be a proper punishment for me, right? Because it would correspond to the subject. But anyway, this longitudinal polarization. Longitudinal polarization has this form k for zero component and omega for space component. And in the limit where energy much larger than mass, mu, which tells that you see that correction is proportional to mass. However, when you consider amplitude involving longitudinal quanta, then you will see that at least for neutral vector field, you have this condition of transversality. The current with which vector field interacting is conserved. So you have the zero, and that's why singular part goes away, and then there is a kind of smooth transition to mu equals zero, and it is kind of in the theory of photon. But when you have non-abelian case, then k mu acting on amplitude gives zero only if it's other indices multiplied by physical polarization. So it's non-zero once it's written this way. So then you can calculate that you see from this formula actually already that if you take one, okay, you can take k mu away. If you take second, then this stuff remains, and then you have a product of this term proportional to mu to the term divided by mu. So I mean, you have a finite limit at mu equals zero for two non-abelian quanta. They of course should be different, not in the color space. So. If you have more than two, and we consider annihilation of fermion, anti-fermion into some number, if you have more than two, then it becomes singular. So each extra photon gives you extra g divided by mu additional energy divided by mu. Okay, so okay, no, this could be formulated in more concise form if using this so-called Stueckelberger substitution, because you can substitute this Parka field by field A mu, which is taken again in radiation gauge, in Coulomb gauge. So A mu by construction contains only transversal component. So then all longitudinal stuff live in matrix S, and mass term becomes just d mu s dagger, and it is no, it's one possible parameterization of S in terms of this field, which correspond to longitudinal polarization. So you see that it is nothing but this SU2 cross SU2 chiral Lagrangian for pi, and it is clearly non-normalizable. Okay, again, worth of recollection that we were thinking how we can make it normalizable. The simple way was to say, let's go from this nonlinear sigma model to linear sigma model to add this extra sigma field, and then the theory is normalizable. But we saw about this regularization, and we did not realize that it is, at this point, this additional sigma field coincides with the Higgs field of Weinberg paper. And Weinberg paper was 68. And what we are doing, that was 1970. The published was in 71. So again, you see, I mean, it's a missed opportunity. So, okay, I should fall down. Okay. Now, next part we did with Jülich was considering, no, I mean, it is already 73, so I mean, already Hoft showed that the theory is a Weinberg model, as we called it before. It's a normalizable model, and we considered limitation for the mass of charm quark, okay, which was not discovered yet, but no, but it was suggested by Jim, what mechanism, and here it is this expression for KL goes to mu plus mu minus stuff, and it was kind of theoretically more involved calculation, involves some triangle diagram, because you have Z boson goes to W boson and then to mu plus mu minus. But limitation was not that great, because here it's only this 9 GeV, and you see from notation P prime, it is what's called C nowadays, and P was called U quark, but it's that old. Okay, from KS mass difference is much better, much stronger limitation, and you see that it is this 1 GeV limitation coming from this. But okay, it was published in this Jet letters, so as usual, it's not very well known result. Say much more known references to Mary Kay Gaillard and Ben Lee, who did a little bit later, but I mean, essentially the same stuff. It was the discrepancy between us was about the first process, K goes to mu, and then there was some number of papers trying to unravel what was going on. Eventually, I believe Mary Kay with other involved Robert Schrock, and they found what was kind of original reason for, so our result was correct. But technically, I mean, in terms of application, it was not crucial. Okay, now I'm coming to kind of more modern history, which goes under the name SVZ. Here it is the picture of 1999 at APS meeting, where we got this Sakurai Prize, and it was kind of covering different topics, so we divided which topics. I believe that, I mean, both Davids and Fleck got Sakurai Prize before the Nobel Prize, right? 86, if I remember correctly. But anyway, my part in 99 meeting was to talk about penguin, about this. So I'm repeating myself. Here. So let me remind you a little bit about this particular problem that, I mean, what we started to do, we considered correction due to strong interaction to weak process. And no, I mean, in particular, no, it was not only this, but I would say that outstanding problem there, it is this ratio of Ks goes to pi plus pi minus to K plus goes pi plus pi 0, because this ratio, it is for the width is 450, while even if you take a square root, it is still a big number. And the original Lagrange Hamiltonian does not contain this crucial difference between delta I equal 1/2, which is first upper process, and versus 3/2, which is the second one. So particular QCD analysis for this purpose was done again by Mary Kay and Gaillard together with Ben Lee, and independently by Guido Altarelli and Luciano Maiani, and it is 1974, and they kind of sum up all this logarithmic behavior. The parameter here, it is mass of W boson, 80 GeV, and so you have a ratio like 80 GeV over, say, lambda, whatever, so in principle it's a large log. However, while they did this summation, numerical effect was kind of rather small. I mean, it was indeed enhancing delta I equal 1/2, but not much. Okay, so another scale in the theory, it is quark masses, heavy quark masses. Okay, in 75, when we did it, say, T and B was not known yet, but C quark already was discovered. After in 74, so we were talking about distances of OMC, and we found that analysis of Mary Kay and Ben was missing effect associated with this heavy quark mass. Particularly, the belief was that due to G mechanism, you always have like MC square minus mu square divided by a large scale, like MW square. And then it's negligible, and it was not considered. However, while it's true for normalization point above MC, for momenta larger than MC, it's not true for momenta smaller than MC, implying that MC is large mass indeed. Because below MC it is log. MC over, okay, you can put a mu if you go all the way down, but okay, if you are still not all well down, it would be mu much smaller than MC. And it is what this log which we are accounted for. Okay. So what was interesting that not only it is a new type of log which was accounted for, they involved new stuff which was not before, because electroweak theory was based on left-handed quark. And this particular log is involve gluon and involve right-handed quark. So effectively, you have a vertex where before it was like current multiplied by current, now it is density multiplied by density, which involve right-handed quark. So, I mean, two left-handed and two right-handed quarks are in the vertex. Okay. And because it involves gluon, that automatically delta I equal 1/2. Okay. I will show the diagram. But the last point is that there is another stuff which close to what was mentioned today, that there is a kind of scale associated with the coefficient between quark mass and m pi square. And it is 2 GeV, which is, I would say that in certain sense it's a large number. So I mean, parametrically, m pi square proportional to p. So coefficient, this instead of 2 GeV, it could be, I don't know, 100 MeV or whatever. It happens this way, and it is like a vacuum average, right? For psi bar psi, and it provides this large number. And we played this in the sense that these new operators which appeared would be given enhanced matrix element, not due to logs, but logs would be responsible for coefficient for those operators, but matrix element would be enhanced. Okay, and we based our consideration on this. So, okay, the idea of small quark masses actually was new at that time in 75. So it was paper by Harry Wheeler and Murray Gell-Mann about this, and for us it was influential paper, and we tried to use it up. And also, I mean, we published kind of, again, jet letters, and then we tried to go to nuclear physics to publish a longer, not much longer, but still more longer paper, and it was not an easy way. So it took like a year and a half. Okay, and you know who was our savior? Yeah, here, right. David Gross was on editorial board on nuclear physics, and he stopped the process by publishing without any changes. I mean, this paper. However, we were so much kind of exhausted with this 1 year and a half that we sent our more detailed paper to Jet for Gain. Okay. Lev Okun, who was kind of helping us, he took special agreement with Lifshitz, who was editor of Jet, to give us twice the volume of normal article. Paper was in short supply. Okay, even twice the volume was not enough for us. I mean, however, anyway, it appears there, but again, it's not much known, probably because of Russian edition. And kind of, I would say that this Mary Kay was the one who kind of broke the ice of mentioning, you know, this idea to the world in her review. And she also collaborated with John Harris, Dimitri Navopoulos, and Serge Ruda in paper for B decades, where they applied also this kind of penguin. And here, our original diagram, I mean, the way it was written, you see this triangle which gives you gluon. Okay, and below it is the way it's written in the paper for authors. No, I more like this picture where John drawing in on the blackboard. You see, it's very and he told the whole story about behind this. I don't know, probably you heard it, that he had a bet with Melis Franklin about dart game. He lost the bet, and he, as a result of the bet, he was enforced to put the name Penguin in his next paper, and he did. So okay. Now, it's what I already told about. Here, my kind of essentially last piece of recollection, because you will hear more about SVZ from Misha Schiffman today. So it's not a threat. It's just to give you a joy of listening of him. But anyway, here it is stuff which goes about this association of confinement with CP invariance, particularly about theta atom. I mean, today was, I mean, in particular, Michael was talking about the theta atom, and indeed it's kind of non-trivial stuff. In particular, I mean, what we found and what was crucial key for us is to associate it with U1 break. No, I mean, this U1 breaking of U1 symmetry. And the reason why it was a doubt, it was that technically, say, in instantaneous approximation, it comes from long range. You have expression for this theta atom. which is total derivative, and then the result non-zero only because you have integral over surface non-vanishing, right? Okay, but you can say that confinement tells you that nothing is like stuff. And the people who kind of argued against it was in particular Sasha Polyakov was the one. And in his 2+1 theory, he had an opposite example. Where theta dependence disappeared. Okay. Another person who argued about this was Peter Minkowski. I'm not sure if you noticed, but he recently repeated this. Recently. Yeah, so you see, he never gave up. Okay, so interesting enough, I don't know. As I try to explain, I'm trying to quote ourselves from this paper. Our final result complies with the conclusion of CP violation, so the most readers can justifiably lose interest in the paper at this point. Because we did try to convince ourselves that it's indeed happened, and we managed to convince, but we were not sure if anybody else needs to be convinced about this theta dependence. Okay, so particular in this paper we derive this stuff. It's vacuum average, but here it is a real amplitude with CP violating. You see, it's algebraically related to theta dependence, and it was kind of, in terms of limitation for theta, it's more useful was, say, anomalous dipole moment for neutron, right? But you see, conceptually, that's just demonstrating that the physical amplitude depends on theta was sufficient at this point. Okay, I'm not talking about this, but in particular, in this paper, we try to modify, this originally Frank and other people's suggestion about axion, because once we have the CP violation, you need something. Original axion did not work phenomenologically, so we suggested what's called now invisible axion. So this name, KSVZ, K is for Kim, who independently did this, even actually published before us. But I think in your picture it was present, right? So okay. So I'm showing, yeah. Yeah. But I have one more slide, but not about much. So, but I still try to use this opportunity. Try to be thankful to organizers that give me this opportunity to share the collection, and also to Yurik, Vali, and Misha for our long-term collaboration. Of course, I also would like to mention that I am grateful to my advisors. So my first advisor was actually Viktor Galitsky. I'm not sure that many of you know the name, but probably some do. He was a very deep person, and he was, for a few years, he was in Novosibirsk where I was. And he was the one who asked me what I like to do. I said that particle physics, and he was kind of in rather good relation with Pomeranchuk. So he sent me for graduate studies, sent me to ITEP. Pomeranchuk said that he is not taking new grad students. It was a few years, last years of his life, he was already diagnosed with the cancer. But anyway, but I can choose from people in the group. So my advisor was Boris Yofe, who died last year in the age of 96. Galitsky died at the age of 56. But he was the one who I think kind of didn't realize himself. He was in Migdal group, and in some way, he was a person who didn't realize himself fully to the extent of his depthness. Particularly, I remember when he came to Novosibirsk, he was, it was beginning of 60s, he was still fresh on, BCS. So he believes that they missed superconductivity discovery because of Migdal. Because Migdal was, kind of the head of the group, they should do whatever he said. And guys, he has particular ideas about interactions with relatives or whatever. Okay, and he could not forget it. And he went to, after high school, immediately went to the front. So partly, I think it contributed much to his early death, because he was in this Kursk battle during the war, so he was heavily wounded. So, So anyway, it's, I'm sorry that I've taken you to all this, but I appreciate your attention to listen to all these recollections. Thank you.
You mentioned some early attempts in Soviet Union to find a theory which, with reasonable ultraviolet behavior. And there is one paper that you did not mention. That's a 1959 paper by Anselm. A four Fermi interaction in 1+1 dimension.
I agree. This was an early paper, earlier than others, I knew, of course, about this paper. Also, Anatoly Larkin, who later was, in Minnesota with us, he continued this activity in 1+1 dimensional theory, where this was asymptotic freedom, right? No, I'm not sure, but you see, I think that, look, even this kind of stuff like Ulrich's paper or Terentiev and Vanyashin paper was not taken, really to appreciation, right? So there's no wonder that, this two-dimensional stuff was not also considered that seriously. Of course, it was. I mean, people reacted that it was counterexample, right? To say more close to today, that, for example, with Misha Schiffman and younger guy, Sasha Monin, our recent publication was about considering kind of calculation beta function using instanton as kind of as a tool, because it also allows to deviate this kind of imaginary part, zero modes, non-zero modes for instanton, but in this sigma model, which 1+1 dimensional model, this that pole, which gives contribution of the opposite sign, it's again the stuff with no imaginary part. So it's very much similar to this kind of Coulomb Coulomb gauge calculation by Hliplovich. But much simpler, because you have that pole has no imaginary part, and it has opposite sign, and it's the reason why it was. Yeah.
Actually, you've been an ideal.
Yeah. No, I think that I fulfill the time. Yeah. Yeah.
Well, I'm going to really. I'm missing the thing about the imaginary part. Normally you calculate. We're talking about the beta function.
Yes.
Right. So normally you just calculate the thing. You could do it in Euclidean space. So where.
No. You can do it in Euclidean space, that's true, but you can consider this particular diagram. You always can say that it is a subject of dispersion relation. Yes. Okay, dispersion relation relates the part you are calculating, real part, you're right, through integral of imaginary part, right? And because imaginary part is sign definite, then you know the sign of real part as well. So in imaginary part is like in simple example is like a constant. In real part it would be log, but coefficient for the log would be dictated by, you know, the sign of the log would be coefficient of the
So it
log.
was one step away.
Yeah, right. But it is essentially the same argument which I think that original Landau argument that why it's generic. Because imaginary part is always, in this sense, positive, and in this way, you always have screening, not anti-screening.
Okay, so what I was missing was it wasn't the presence of the imaginary part; it was the sign of the imaginary part.
Yeah.
That was.
Yeah. The imaginary
was the
part is
physics
positive
there.
data. It gives you sign of the log, coefficient for the log in the real part.
Okay. So normally, you know, when you ask a question, you say to the students, if you have the question, nobody in the room understands it. I'm convinced I asked the question and everybody else in the room understood it.
Okay, good. No, but
You're
look,
a good class.
I think it's just, I should say that it is a little bit, you know, kind of growing up in particular school of thought, right? So I would say for people in our circle there, this approach to relate, to have in mind this dispersion relation and the sign was kind of extremely natural. So because it was maybe less formal, I am not sure.
Any other questions? See, I wasn't shy.
Yeah.
Okay.
So, not so much a question, more, I'm afraid, a comment. Interesting comment. You talked about the delta I equals a half rule and the role of penguin diagrams. And as you correctly said, the first people to look at this were Lee and Gaillard and Alterelli and Maiani. So I was in Rome at the time, and when Alterelli and Maiani produced their first paper,
Yeah.
they their preprint version, they ascribed a big contribution to the so-called penguin diagram.
Yeah.
And then Ben Lee and Gaillard pointed out that Maiani had forgotten the Jim mechanism.
Yeah.
And so the contribution to that diagram became much less.
Yeah. Right. But you're right. But when I'm referring to 1974 analysis, it was already not there, right? Because what
That's
you're
right.
talking, yeah.
That's right.
I
It
did not
got
know the
corrected by
details
Ben
of
Lee.
history, right? So it is your responsibility then.
Sorry, I didn't hear.
No, I mean, because in this way, to realize that you still have different type of log because of this range. Yeah, for us it was crucial.
That idea was certainly not there. That was surely yours.
Yeah,
But,
I see.
Historically, they got it wrong, and it's amusing that he forgot about the Jim mechanism.
No, but it was the reason why we had this problem with publication, because this argument with the Jim mechanism, that it should be a small effect, was for every expert, and the paper went through everybody. I mean, our efforts, and everybody kind of was not convinced by this, right? So I think that part of the blame is for us, because we wrote it in the way that people could not kind of understand, so it is still, I still should fall down. Yeah. So, for?
What is the present situation with the delta I equals 1/2?
Yeah, okay. Yeah, I decided not to go to details, right? Okay, let me answer this. Okay, the approach which I did not discuss much, and it is a lattice calculation, right? Right. And it is a long history about this calculation. It occurs to be very difficult problem for lattice calculation. And I think that lately, I mean, they managed to come to result comparable with, phenomenology. But it took, I don't know how many years, starting from Michael Kreuz's early calculation, whatever. Personally, I think that the part which is important and in some way not reflected in lattice calculation is from which distances effect is coming. So you see, I try to argue that it is, you see, it's a sensitive to which distance. So it's 1 over MC, and if I would be a lattice calculator, I would be trying to identify whether it indeed comes from there or not, just to have a real understanding what's going on. Of course, now in the age of artificial intelligence, you do not need to understand how it's going, but I am still in the old time and trying to understand. So my impression is that in this way, phenomenology, which we did, was kind of, we worked through all decays, K decays, Hyperion decays, whatever. However, it was phenomenology in the sense that we put coefficient for this new operator by hand. However, for example, where it was important, say epsilon prime or epsilon. Because when people did not account for this, they predicted epsilon prime or epsilon smaller than it was. In this logic, it was natural to have this. So my impression is that kind of essentially it's not completely unraveled. I mean, at the moment.